So today we're going to look at planes in 3 dimensions. So we know that a line can be uniquely defined by 2 points or 1 point in a direction vector. It doesn't matter if it's a 2-dimensional line or a 3-dimensional line, it's the same rules. In 3 dimensions, we can also define something called planes. To define a plane, we're going to need more information than a point and a direction vector. We'll see we'll actually need 2 direction vectors and a point. But first, let's talk about what is a plane. A plane is essentially a slice of space. So if you imagine holding a piece of paper at an angle, and it might help you to actually hold a piece of paper, and if you extend that piece of paper out in your mind in all 4 directions infinitely, that's a plane. If you tilt that piece of paper at a different angle and imagine it extending out in all 4 directions, that's another plane. And you can infinitely tilt that piece of paper in different ways, extend it out in all 4 directions, and you would get all the infinite planes that exist. Okay. So here we can see, I've just used the apple graphing tool, and I can spin it around in 3 dimensions, and they have graphed a plane for me. Okay, so they've only graphed it to the edges, but we can see that it's really a slice. It's infinitely thin. If you look at it one way, it looks like a line even. But it's just a slice of space there. So the question becomes, why do we need more information than a direction vector and a point? So if you think about holding up a pencil, and if you take your piece of paper and think about slicing that pencil by putting that piece of paper right next to it along the edge, okay? That's one way that the plane could go through the pencil. If you tilt your paper a little bit and make the paper go through the pencil a different way or touch the pencil a different way, that's another way a plane could go through the pencil. And you can keep tilting your paper all the way around 360 degrees and keep just slicing that pencil. And those are all planes that pass through. And in fact, there's infinite planes that pass through the one line, in this case, your pencil. So just having enough information to define a line is not enough information to define that plane, because we know that there's infinite planes that would pass through that one line. So the way that we stop the piece of paper from being able to essentially rotate around the line is we create a second direction vector. Because now if you're holding 2 pencils, not parallel to each other, the paper could no longer rotate around the first pencil because the second pencil would be stopping it. And I might try and draw this out a little. Okay, so there's my first pencil, and my piece of paper could have cut it a bunch of different ways. And now I have my second non-parallel pencil, and now the only way that the piece of paper is going to lie on both those pencils is if it looks like that. Okay, it can no longer twist, it can no longer have gone sideways, because then the second pencil wouldn't have been on it. There's only now going to be one way for that paper to lie on both those pencils, assuming that there was some sort of starting point. So how do we actually create equations for planes? So I've told you that we need 2 vectors, and they can't be along the same line, because then they wouldn't be more information, it would just be more of the same information. So they have to actually be 2 non-parallel vectors, which really for us means they cannot be multiples of one another. So we need those 2 non-parallel vectors, and we need a point. And to form equations, it's actually very similar to what you've already done. So for the vector equation, it's going to be r equals the point, because we still need one of those, times plus t times your first direction vector, your m1, plus s times your second direction vector, your m2. So it's really like a line, just we've added on this extra bit of another direction vector with another parameter. And just like before, t and s are elements of the real numbers. So there's the vector equation, very similar. If you can do a vector equation of a line, you can do a vector equation of a plane. For parametric equation, same idea as parametric equations of lines. All you're doing is you're splitting it up into the x component, the y component, and the z component. So same thing, just this time, of course, there is that third bit to it. For symmetric equations, there are no symmetric equations for planes. And the reason is because symmetric equations is what you get when you isolate the parameter. But here there's two parameters, so we can't isolate them both at the same time, so there's no symmetric equation. So let's go through an example here. They want us to find the vector and parametric equation of the planes containing these two direction vectors and that point. So the first thing you should do is just quickly check and make sure the direction vectors are not multiples of each other. Right? To get from direction vector 1 to direction vector 2, we would multiply by 4. Right? 1 times 4 would give you 4. If you do 3 times 4, you'd get 12, which is not a 7. So they're not multiples. So that's perfect. So to do the vector equation, all we're going to do is write it out. So it's going to be r equals the point, which in this case is 4, 11, 6, plus t times that first direction vector, our m1. And the order of the direction vectors actually doesn't matter. Plus s times our second direction vector, where t and s are real numbers. So there's our vector equation. And we can do parametric next. We're just going to split it up into the x, y, and z. So pause the video and give it a try. And there is our parametric equations. Example 2 tells us to write the parametric equations of the planes containing, or of the plane containing the points A, B, and C, and then determine whether point D is on the plane. So we're going to leave this last part alone for a little bit. First, we're going to start by finding the equation of the plane. So we need two direction vectors. So let's do BA and AC. As long as they're two non-parallel direction vectors, it doesn't matter really which points you subtract. So take a minute, find BA and AC. So now that we have our two vectors, you just want to quickly make sure they're not multiples of each other, which they are not. So now we're going to use these two vectors and one of the points. Doesn't matter which one, I'll just use A because it's the first one, why not? And we will come up with the parametric equations. There we go. So x, y, and z. It's going to be the point plus t times the direction vector plus s times the second direction vector. So there we have the parametric equations. So that's the first part of this. The second part is determining if D is on this plane. So in other words, determining if D would satisfy these equations. Because remember, D has an x, a y, and a z. So what we're going to do is we are going to sub the 14 in for x, the -2 in for y, and the 20 in for z. And we can simplify each of these because there are two numbers there that we can combine. So I'm just going to move the 1, the 4, and the -2 over. So I would get 13 equals -4t plus 5s. That's my first equation. When I move the 4 over, I would get -6 equals 4t plus 2s. That is my second equation. And my third equation would be 22 equals -9t plus 5s. So what you have to do next is you have to choose two equations because there's two unknowns, and we always need two equations to solve for two unknowns, and you're going to solve them using substitution or elimination. Doesn't matter which of the two equations you use, but choose two and set the third one aside for a couple minutes. So I'm going to choose equation 1 and 2 because there's these 4 t's that add up nicely, and it's going to make elimination really nice. So I'm going to solve equation 1 and 2. And it always helps if you guys write what you're doing, especially when we're working with multiple equations. So equation 1 and equation 2. And I'm going to use elimination because these already have the same coefficient just with opposite signs. I'm going to add the equations. So 13 plus -6 is 7 equals, these would cancel out, so there'd be a 0 left. And then 5s plus 2s is 7s. And 7 equals 7s means that s equals 1. Okay, so there is my s value. And now I need to figure out t. Okay. And once again, only use the two equations that you've chosen. We're pretending that 3 doesn't exist for right now. Okay, so we need to solve for the t value. So for instance, we can sub into equation 1. And when we do that, we get that 8 equals -4t. So that means that t equals -2. So now we have an s and a t. And you might think there's an s and t that exists, that means the point lies on the line. That's not actually what it means right now. What it means is that those first two equations do have a solution. But we now need to check to make sure that they work in the third equation. So now that third equation comes into play, and we're going to do a left side, right side check with it. So that's the final step here, is check in whatever the equation you didn't use it is. In my case, I didn't use equation 3. So I'm going to do left side and right side, because that's what we always do for checks. And I'm going to plug in my s and my t. My left side's already 22. For my right side, -9 times -2 plus 5 times 1. So that would give me 18 plus 5, which is 23. So we see that left side does not equal right side. Therefore, point D is not on the plane. If the point had been on the plane, then the s and t would have satisfied all 3 equations, not just the first 2.